Sir, we can't hear you.
I'm very sorry because I will be for about 5 minutes red.
Ew. Oh my gosh, ew.
I thought I unmuted it anyway. Let's okay, let me do it again. Okay. Anyway, the floor ready. And as I was saying to myself, this is the secant passing through the tangent and another point on the curve. It's just an arbitrary point. And so we get the y coordinates f of x for x and f of x plus h for x plus h. And then if we compute the change in y over the change in x, it will be on f of h minus f of x and x plus h minus x. And so we have this formula here, the encircled one, for the derivative of a function where h approaches 0. As h approaches 0, what happens is that the secant lines get closer and closer to the tangent line. Our point gets closer and closer to the point of tangency along the curve, so the approximations get better and better. So that in the limit, we get the exact slope of the tangent to the curve at the point. So that's how we define the derivative. Now, in this chapter, we are going to deal with functions of two variables so that we no longer have a function like y equals f of x. Okay? Rather, we will have a function g, and g now is in terms of two other variables, x and y. Now, to evaluate this function, if you've studied the book, okay, or read the material, you all you have to do is if f is given, the formula for f is given, which is in x and y, some x variables and y variables will appear in the equation. All you have to do is substitute x equals the given value and y equals the given value. So that instead of having an ordered pair, you will have an ordered tripole. Instead of having a two-dimensional coordinate system, you will have a three-dimensional coordinate system, and thus you will have to add a z-axis aside from the x and y axis. And instead of a curve right here, you will have a surface. Now, I won't be giving you problems where you have to plot points on the three-dimensional coordinate system, but I will just generalize how to locate a point on this rectangular coordinate system. So what you do is locate, say you want to find a point ABC. Excuse me. Wait lang.
Oh, cute. What the heck?
I'm very sorry. So where were we? As I was saying, so what we do is locate A along the x-axis. So That depends whether it is on the positive side or the negative side. So the arrows point towards the in the positive directions here. So you find A, say here. Okay, that is A. Find B, and then locate AB, which is on the XY plane, and then that AB will be a projection of the ordered tripole ABC on the XY plane, and C will be the vertical distance. And if it's a point on the surface, position is Z equals f of xi, C must satisfy C equal f of B. So instead of having like as in a single variable function, y equals f of x, where you evaluate it at A, so you have B equals f of A. You have three coordinates now, A, B, C, where C equals f of AB. Now, it turns out that when you evaluate the partial derivatives with respect to x and with respect to y, since it's now a two-variable function, they will just be geometrically the slopes of the tangents to surface a point ABC here. And the one drawn there is slope that goes in the or is parallel to the x direction. And then the partial with respect to y will be represented by the slope of the tangent to the surface at the point ABC parallel to the y direction. Okay, I've given uploaded two videos there in the module, which will give you the geometric interpretation and can be better illustrated there because of the high-tech tools that they use there. So just to illustrate quickly the definition of the partial derivatives with respect to x and with respect to y, notice here in the definitions that one of the variables is while the other variable changes, since we're evaluating a partial with respect to x and a partial with respect to y. Looking at the partial with respect to x, that's how we denote it, f subscript x, or sometimes this symbol here is read as partial. So here we have partial of f with respect to x. Use partial because we use partial because there's another derivative, and actually, this is beyond the scope of the course. There's a total derivative. Now, the partial derivative with respect to x is defined by this page. It's almost the same as ordinary derivative for single variable functions, except that the function f is in terms of two variables now. You observe the numerator, you see that y is not changing because we are differentiating with respect to x. So what is only is x from x to x h by an amount given by h. And this then will represent the slope of the secant line in the direction of x, as shown in the figure here. So if you look at the figure, this is the point AB, and this is the point A plus HB. Now, y does not change, so B is fixed. And what happens here is that we move only along the x direction. So if you locate the corresponding point on the surface for A plus H, then you have this point and you have the secant line. That secant line will approximate the slope the tangent line. The tangent now is in the x direction. And what you do is you let A approach 0, this is the distance between those 2 points. And if you let H approach 0, the secant lines will get closer and closer to the tangent line, so that in the limit, we have actual slope of the tangent in the x direction. And we have a similar geometric interpretation for the partial with respect to y. Instead of moving along the x, we're now moving along the y direction. So that our tangent here presented the green line, okay, is again tangent to the surface at point tangency, parallel the y direction. And the secant line here gives us the numerator for the partial derivative with respect to y. And what we do is let the points approach this point along this curve here. Anyway, you need not be that concerned with the geometric interpretation. What is really needed in this course is for you to know how to find the partial derivatives, which we will do now in this example. Okay, I hope I'm not muted. All right. So,
You're
okay.
good.
Yeah, thank you. We won't use the limit definition. Remember, in differential calculus, you first started with using the limit, and then later on, your teacher developed some formulas like power rule. We have some difference rule, chain rule, product rule, and the others. So instead, we will be using those rules. And the only difference here is that we have two variables. But since we're only getting the derivative one variable at a time, all we have to do is just keep the other variable or treat the other variable constant. So looking at the equation there, z equals f of xy equals 2x squared minus 3x squared y plus 5y plus 1. How do we get the partial derivatives with respect to x and a? So looking at the first term, we differentiate that with respect to x, and that is easy. It's just in terms of x alone, so just 4x. But if you look at the second term, it has two variables. So how do we differentiate that with respect to x? Now you think of y as though it's just a constant. So you can think of it as though it was, let's k or 2 or any other constant. Then if you differentiate, all you have to do is, since the derivative of a constant times a function is simply the constant times the derivative of the function, all you have to do is differentiate x squared. And then you multiply it by the other terms, which are constants with respect to x. So we have 4x minus 6xy. Third term, 5y, with respect to x, y is a constant, so its derivative to 0. Similarly, 1 as a derivative of 0 with respect to x. So this is the partial derivative with respect to x. The partial with respect to y, we derive by treating x constant. So differentiating 2x squared, its derivative with respect to y is 0 because it contains no y. X is a constant, so a 0 derivative for that. Second term, we differentiate with respect to y. The derivative of y with respect to y is equal to 1 times the constant 3x squared. So we have minus 3x squared or negative squared. Derivative of 5y with respect to y, 5. Derivative of 1 is 0. So those are the partial derivatives of the function with respect to x and with respect to y. Let's have another illustration. So given that exponential function, find the partial derivatives with respect to x and y. Note that the exponent there is now a function of two variables. Before we can answer this, let's recall the formula of the derivative of exponential function e to u with respect to x. By the chain rule, it's e to the u, derivative of u with respect. So applying that, we have the partial of z with respect to x, or simply f sub x. You may want to omit the ordered pairs. Just simply write f sub x. Okay, this will be given by e to the x squared plus y squared. And then you differentiate x squared plus y squared with respect to x. And if we are differentiating that one with respect to x, y squared's derivative will vanish. So you have only the derivative x squared, which is 2x. Or
Sir,
simply,
question.
yes?
The AF over AX, that's the same as F sub X?
Yes.
Okay.
You can also write this. Okay? This derivative,
Sir,
we
what do you call
have,
that symbol?
it doesn't matter what symbol, preferably the one more convenient for you to write. Sometimes you might find writing this one hard, difficult. So just use a subscript,
Okay, sir.
as I will also show later. We go to especially second order partial derivatives. And then doing the same for the partial derivative z is y, which can be written as partial with respect to y. And also it is way. Or again, you subscript x. And to get it, we use the formula for the exponential function. The derivative is itself e to the x squared y squared times the derivative of exponent, this time with respect to y. Sorry, I wrote the wrong. It should be with respect to y. So differentiating now this one with respect to y, x squared will now be constant, so this will be 0. And then we differentiate y squared y. We have 2y e the x squared plus y squared. So is there any question? Okay, let's try another. Okay, let's go to second order differential, partial derivatives first. Okay, in differential calculus or the calculus of single variable functions, we also studied the second derivative of a function and how it relates to the graph and the first derivative. Now we also have similar concepts for multivariable functions. So that means we will have 4 second order partial derivatives since we have 2 variables, x and y, 2 times 2. So we should have 4 possible pairs and thus 4 second order partial derivatives. Now let's look at the first. Now the first one here, let me start from the right. F sub xx means you're differentiating first the function with respect to x, and then the result, you'll be differentiating it again with respect to x. So it's also stated this. You differentiate with respect to x the derivative of f with respect to x. The symbol is just the same. Fx and then. Now times includes, write fxx simply as this one. Partial squared f partial x squared. It's just a shorthand notation using that symbol for the second order partial derivative there. Similarly, we have f of yy as the derivative of y. So the derivative of f with respect to y with respect to y. So you differentiate f partially with respect to y to y. And this is the other notation for that. We all have the cross derivatives, and we have two. We can first differentiate with respect to x, then with respect to y, given by this one. Or equivalently, we just write f sub xy. So you read from left to right. So derivative first with respect to x, then y. But the other notation reads the other way around. You read it for right f. So whenever you see that notation, differentiate with respect to okay, you first differentiate with respect to x. Okay? And then with respect to y. And we just write it in this order so that you have to read it from right to left when you evaluate. Similarly, this one reads from right to left. You take the partial first with respect to y, then with respect to x, as given this. Y, then x. Or more conveniently, we just write f sub yx. Left to right, so y first, then x. Now anyway, let me illustrate the computation with an example here. This one has a typo error. This is just partial x squared. So we differentiate z or f with respect to x twice. So let's do that. First, partial of f with respect to x. We treat y constant here. So term, the derivative, y is constant. We differentiate with respect to x, x cubed becomes 3x squared. And constant y. This becomes 0, and this becomes 0, since they are all constants with respect to x. Let's first get partial with respect to y, then the second order derivatives. First term, okay, with respect to y, x cubed becomes constant. So we have x cubed plus 1. The derivative of y with respect to y is 1. Then second term, with respect to y is negative, power formula lang, negative 8y cubed. And then this is constant. So we have the first order partial derivatives. Now let's evaluate x, x. That means we are going to differentiate partial to x with respect to x. And then we treat y constant again. So differentiating x squared, that's x. So we have x. Partial with respect to, okay, y with respect to y. So we differentiate partial with respect to y given this one with respect to y. And x is constant is from 0. And this one differentiating is 3y squared times negative 8. So negative 10 4y squared. Now the cross derivatives. F xi. So to avoid confusion, okay, let's use this notation instead. So x first, then left to right. So we already got the partial with respect to x. So now go to differentiate with respect to y. X is constant. So we differentiate y with respect to itself. 1 times the constant. So 3x squared. And then finally, f by x, y first, then x. Partial with respect to y, and then with respect to x. Now, with respect to x means y is treated as a constant, so this becomes 0. And then we differentiate x cubed plus 3x. And observe that the two cross derivatives are just equal. In fact, that is always true for continuous two variable functions. And we won't be proving that, but we will be assuming throughout the course that the two cross derivatives are always equal. But anyway, whenever asked for each, you have to show a solution for each. So is there any question?
Sir, can you clarify how to get everything after fx and fy?
Okay, here's fx, right? So here's fx.
Yes, sir.
So that's the first one. And then we're going to differentiate it again with respect. So we have it here. Now fyy means fy first, which was gotten to be this one. And then another time with respect to and so on. Now, is the order in which we do it clear? Or are you really confused with getting the derivatives of the functions in the parentheses? Clarify your question.
Medyo gets, sir. Medyo lang. Not fully, pero medyo gets.
Okay. Dito, actually, ang second order partial derivatives, you're just differentiating first order partial derivatives. So if you know how to do first order, it shouldn't be hard to do second order. The only confusing thing here is the order in which you do them. So I'll illustrate one more time. This is this the same? This one. F of xy equals sine of xy. Do you still recall the derivative of sine? It is positive cosine. Now, if we apply the chain rule, we know that the derivative with respect to x of e to the u, sine 2 is equal to cosine u dx. And if we do it with this derivative sine becomes cosine u dy. Our partial derivatives, we have two variables. U can be in terms of both x and y. So let's do this. Okay. So here's our option. We're now differentiating with respect to x. First order muna tayo. So the derivative of sine is cosine. So let me copy. Just replace sine by cosine. And then the rest would just be to differentiate this term with respect to the variable in consideration. So we're going to differentiate that with respect to x. Now, what's the derivative of xy with respect to x? Anyone?
Why, sir?
Why? Because, I'm asking why. Because
Uh,
y is a constant. So we're going to differentiate this x, and it's just 1. And then times the constant 1. Okay? So we have y out. Rearranging gives y cosine x. Partial with respect to y. It will be the same, copy, change to cosine, but differentiate now, this time, with respect to y. So this will be constant, and derivative y with respect to y is 1. So we have times x outside. Or x cosine y. Those are just the first order partial derivatives. Let's now find all the 4 second order derivatives. Now let's start with the non-cross derivatives. So fxx, how do we get this? We differentiate with respect to x, which one? This one. Correct? And we already got that here. So I'm going to write that partial with respect to x. So yan. Kinopya natin ha. And then meron isa sa labas, this one. So I'll be differentiating this one now, subscript x, meaning I'm differentiating it with respect to x. So this function is going to be differentiated with respect to x. Y is treated as constant. Now this is a product, so that means you have to recall your product rule. Do you still remember the product rule? Yung meron kang product of two functions, you obtain it by multiplying the first by the derivative of the second plus the second times the derivative of the first. So let's apply that here. So the function, it's y, the first, times cosine y, that's the second. So that will be the first, which is y, times the derivative of the second. And then we're going to differentiate that with respect to x. Ano yung derivative ng cosine? Negative sign. So I'll copy it, replacing cosine its derivative. And then don't forget, you still have to differentiate this. Okay, trying ko lang. Okay, we need still to differentiate this one with respect to x. Okay, huwag niyong kakalimutan kung saan kayo nagdi-differentiate. Anong variable yung dinidifferentiate. So differentiating that with respect to x, y is constant, derivative of x is 1, so we will have y outside. Now we're not yet done. There's another term. Plus the second times the derivative of the first. Second. Differentiate the first. Now, what is the derivative of y with respect to x? Anyone?
Zero, sir.
0. So, vanish lang siya. And implication gives us negative 1 squared. Sorry, what happened here? Okay, negative y squared sine xy. Okay. Next, partial with respect to y with respect to y. So how do we get this one? We are going to differentiate this function with respect to y. And that is already found here. So I will just be copying this one, x cosine xy. X cosine xy is partial of f with respect to y, the first derivative. And then we're going to differentiate that with respect to y. Product rule. First, derivative of the second with respect to negative sign xy. Then we differentiate xy with respect to y, and that would be x. Plus the second times the derivative of the first with respect to y, which is 0. And here we get negative x squared minus. Now the cross derivatives. F, F, y. So here we have to do partial with respect to x first. So ito yon. Let's copy that. Y cosine xy. So yan. And then we're going to differentiate with respect to y. Again, product rule. X times y times the derivative of this with respect to y. So we have negative 9, then the derivative of this with respect to y. So x. Plus the second times the derivative of the first with respect to y. This time it will not zero out. That is 1. So negative xy sin xy plus cosine xy. Okay, if you have any question, just chat, and the rest could work out. Fyx, I should clarify that the two cross derivatives are equal. Okay, I'll be copying already Fy, x cosine x. Okay, just work that out.
So for most cases, the cross derivatives are equal.
Yes, for all functions that are continuous. Now we have a definition for continuity of a two-variable function, but that won't, of course, be included in this course.
Sir, will we be tackling non-continuous?
No, we
Okay,
don't
sir.
have time as well. And before I forget to announce, tomorrow we will still have a live discussion / consultation. So harder exercises will be tackled tomorrow.
Okay, sir.
Okay, let me show. Okay, product rule. X. Then differentiate. Negative times 1. Then x1 respect to x. Y. Plus times 1 derivative of the first. Respect 1. And you get it. So are there any questions still? Then we have none. We go to applications. Okay, let's read the problem. This one is on the Cobb-Douglas productivity function. There's a video in the module that will help you study that. But anyway, let me discuss an example as well. The Cobb-Douglas productivity function is always a constant times a power of x and the power of y. And of course, you really need not concern yourself with that since the function will always be given. Anyway, for your information, the sum of powers of x and y must always add up to 1. The power of x represents the elasticity of labor, or x, and the power of y represents the elasticity of capital, which is Y. Now, given the activity function, let us find, okay, the following. The marginal productivity of labor. Now, what does that mean? The word marginal is simply derivative. So it's simply partial derivative of the function, the Cobb-Douglas function with respect to x. Similarly, we have this one as the marginal productivity of capital. They represent the rates at which the overall productivity is changing with respect to x and with respect to y. Now, here's the question. If the company is currently utilizing 4,000 units of labor and 2,500 units of capital, find the marginal productivity of both labor and capital. The question also that is asked here is, should you say you're some financial advisor, should you encourage the company to increase the use of labor or the use of capital? Now, with this kind of math that we have, we will be able to make the proper decision. We need to get the partial derivatives. Now, if we differentiate with respect to x here, y is treated as constant. So all we have to do is really differentiate it. And if you have the power rule, you just have to bring down and you just subtract 1. And then multiply by the others. So you have this one here. Now, you don't need to simplify, just leave it in that form. You can use your calculator anyway when given specific values for x and y, instead of putting it below, making it positive. Now, similarly, if we differentiate, okay, this one with respect to y, we just have to apply the power for this one. We bring down 0.6, then subtract 1, negative 0.4. That we will have this one. Sorry. Already evaluated. This one here. Now, given those two partial derivatives, we plug in the given 4,000 units for x, 2,500 units for y. So that means you will be using your calculator. You'll be substituting for x and y values, and you will be getting this answer, 4.53 units. Now, the units of labor is not specified. It could be the number of workers, it could be the number of machines that are used to produce a certain product, and units of capital may not necessarily be in dollars. It could be in millions of dollars. So here, they are not specified. We just use the term units, as in areas where instead of specifying a unit of measure, we simply write square units instead of square centimeters, okay, if the measure is not specified. Now, we do the same for the other partial derivative. We plug in the values, 4,000, 2,500, and we get 10.8. Of course, those are approximate to 2 decimals. Now, how do we interpret? Before we answer the question, let us interpret the results. How do we interpret this 4.53? Now here, what is changing is x. Remember, y is being treated or held as constant. So that means we fix production level or the capital at 2,500 units. Now the question is, what happens if we change or we increase the units of labor? This tells us that on the average or approximately, let's use that term, that's more accurate, 4.53 units in the overall productivity, okay, will be added, or the productivity will increase approximately by 4.53 units per unit increase in the labor. So that if I add one more unit to labor, so let's say we produce 4,000 or units of labor, then we expect the productivity to increase by about that 4.5 units. Now, similarly, we interpret marginal productivity of capital. This tells us that per unit change in the capital, fixing the labor at 4,000 units, that will give an increase of about 10.86 units in the overall productivity. So time for decision, which should be increased. Obviously, since there's a greater increase of 10.86 units than 4.53 units for capital as opposed to labor, so we encourage increased use of capital. Is there any question with this application? Now, in the long tests, not all problems are finding partial derivatives. There will be, they call this, applications, and those applications may not necessarily be the ones discussed in class. Okay, let's have one last example here. Let's read. A firm produces two types of calculators each week, X of type A, Y of type B. So this time, the unit is the number of calculators. One unit would mean one calculator, depending on the type. The weekly revenue and cost functions are given there. I won't be reading them. Let's find the following quantities. 1,200 units of type A calculator and 1,800 units of type B calculator. Let's interpret the results as well. Now, first, we need to get the profit function. We are given the revenue and then the cost. Now, we know that profit is equal to revenue minus cost. Yung kung Tagalog, yung kinita mo, babawas mo yung ginastos mo. Makukuha mo yung tubo. It's the profit. Now, since we are given anyway the two, we just have to subtract. And it's not hard to do the math. We just have to subtract. Okay, then this will remain and this will become negative. Mag-negative ang lahat. So if we subtract, then we get this one. 3,600x plus 4,200y plus 2xy minus 2.5x squared minus 2.5y squared minus 1 million. So revenue minus cost. Algebra lang yan. And once you've found the profit function, you just get the partial derivatives. So getting partial with respect to x, we have that. So just showing you, we differentiate this with respect to x. That's 3,600. The derivative of this one is 0. Kasi y yan, constant yung y. And then differentiating 2xy with respect to x, ano na lang siya? 2y. And then this one, just use the power rule, bring down 2, you'll get 5. Then there's 0. They are constants. And then the other one, partial with respect to y. Similarly, we get 4,200 plus 2x minus 5y. Okay? Now, let's evaluate at the given values of x and y. We have the following. So we have the partial with respect to x equal to 1,200. With respect to y, negative 2,400. Let's interpret the results. Now, how do you interpret this one? And like to recite? Because in the exam, I might ask you to interpret the results, and greater weight might be given to that. So you may want to try. How do you interpret that? How do you write that in words? As a mathematical equation, it's very compact. But when you try to interpret it, it takes a paragraph or a couple of sentences. Now, first, you have to know what variable is being kept constant and what variable is changing here. That can be given by the subject here. That tells you you're differentiating with respect to x, so you're changing x. That means you're keeping y constant. So if y is constant, then this is x. You do not increase that number, which is type B calculators. So fixing the number of type B calculators at 1,800 units of production. What happens if we increase by 1 unit the number of type A calculators? The result there tells you that the overall productivity, or that is the profit function here, will increase by about 2,200 pesos. Kada calculator na idadagdag mo sa production mo, i-expect mo meron kang dagdag kita na 1,200 per unit increase in X. Now, similarly, per unit increase in Y, okay? Fixing the production of type A calculators this level, if we increase by 1 unit, what happens at the overall productivity or the profit function here will decrease in the negative value about 2,400 pesos. So para bang anong lumalabas dito? Lugi pala siya pag dinagdagan pa niya ng isa. The thing here is either to decrease the production, that tells you to decrease the production of type B calculators and increase the production of type A calculators. So sometimes in the quiz, you will be asked for a decision to make depending on the results of your computation.
Sir, question.
Yes.
So at a fixed rate of, as fixed number of 1,800, it's already break even.
Sorry?
Kung 1,200 type A is fixed, tapos 1,800 type B calculators, that's already break even. Tapos if you add one more type B, that's when you get lugi. Tama ba, sir?
No, it's not necessarily the break even. The break even is where the profit is exactly zero. And there are a lot of possible values of X and Y that will make that true. Now, you're not just solving for X. If you want to equal this to zero, you'll be solving for all possible combinations. That's why it's not included under this topic, the break even for two variable functions. Mahirap. This tells you nothing about break even, only the rates of change. Okay? So tomorrow we will just have an hour, okay, of consultation and discussion. If you don't have further questions, that will be it for today.
Sir, can you restate the interpretation of the PX and PY sa last ones ulit?
In the module, I think I gave. Did you check the module?
Yes, sir. I have it with me right now.
I'm not sure. I forgot. But anyway, let me interpret it. So this start again with this one.
Sige, sir.
So one last time. Now this one here, what is fixed?
X. Type
No.
A.
We're differentiating with respect to X, so X is changing. So what is fixed?
So type B, sir.
Y. Oh, yes. So this is fixed. So you're not going to change anything about the production level of type B. Now you're interested in this. What happens if I increase my production of type A and not type B? Now this tells you if I do one more, okay, that's why it's marginal. One more, okay, one more unit of type A calculators, on the average or approximately, my profit will increase by that amount. Now you can state that in your own words, or the more formal way to state it is this. Okay, per unit increase in type A calculators, there will be a 1,200 peso increase in the profit. That's as simple as you can state it. Now, similarly for this one, what is fixed and what is changing? Anyone?
Type
You're
A
differentiating with respect to Y, so what is fixed?
X.
Yes, the other one. So what is changing here? So the X is not. So here's the owner of the company, and he's not thinking of, say, changing the number of units for type A calculators. Now he's interested in increasing, okay, the number of type B calculators. Now, how does he interpret this? Well, he sees a negative result. So that tells him not to add one more, right?
Yes.
Because per unit increase in the type B, okay, there will be a decrease of about 2,400 pesos in the profit. And perhaps if you change the values, you might get a positive result. You might want to experiment with different Y values and try to produce positive. In fact, there's a maximization later on. What is the maximum how many units of X and how many units of Y should we produce to maximize the profit? That's under the next module, Lagrange multipliers. Okay, that will be it for today. Are there any more questions?
Thank you, sir.
Okay, I'll just be sending you the set of exercises to work on in the book. Okay, that's it.